Hi everybody! In this lecture we are going to talk about lots of different operating systems. We're going to compare and contrast Unix to several others and see what we can learn about them. So we'll talk about the history of some of these other major operating systems, and at the end we are going to even wax a bit philosophical about where we've been and what we might do with all this knowledge that we've gained. So a short history here of DOS. So DOS stands for Disk Operating System, and very definitely a business-driven enterprise here. So the setup: Bill Gates and Paul Allen were writing and selling Microsoft BASIC, which was a language that was used for development, and they were selling this to some early computer hobbyists. IBM, the giant company, was just finishing up prototypes for their new PC. IBM approaches Microsoft to see if they have an operating system that could run on their new hardware. And this is about December in 1980. Microsoft does not have such an operating system. So what they do is they quickly then license 86-DOS from a company called the Seattle Computer Products. And this operating system, 86-DOS, was written by Tim Patterson, who was only 24 at the time. Microsoft then takes this 86-DOS that they have a license for at the request of IBM. They present it as Microsoft DOS to IBM, who accepts it. IBM and Microsoft then jointly rewrite the version they have, and they both claim a joint copyright for this operating system. And then 1 month before the PC's release, Microsoft purchases all of the rights to 86-DOS. So this is July 1981, and they purchase all the rights from SCP. And that's just 1 month before the IBM takes off and completely blows out the PC market. They completely take over. SCP later sues Microsoft in what is going to be the beginning of a pattern where Microsoft uses its business acumen to succeed over companies. They do a wonderful job in terms of capitalism, in terms of taking over the market. And here is a case where they eventually get sued. Ultimately, Microsoft has to pay $1 million to SCP for what happened because SCP is able to claim that Microsoft concealed their relationship with IBM in order to purchase the operating system that cheaply. So that all happens. So IBM begins sales of the PC with PC-DOS in August of '81. Microsoft, and this is truly brilliant, they get with their license with IBM the ability to begin sales of MS-DOS, which is the same thing as PC-DOS, but it doesn't have IBM-specific drivers. Microsoft sells their version of MS-DOS to all the other OEMs, to all the other original equipment manufacturers that are making competitor computers to what IBM is doing, and eventually who start producing IBM PC compatible clones. So Microsoft is undercutting what IBM is doing by selling the same operating system to everybody else. And eventually Microsoft gets exclusive rights to DOS, so they get them all back from IBM, and then they sell to all the OEMs, which is what secures their place in the market. The last version of MS-DOS was released in 1993, so this would be version 6, and it has huge sales and huge success. Microsoft becomes massively profitable because of MS-DOS in the beginning. So Windows comes out in '85, so Windows 1.0 was November 20, 1985, and it wasn't a very good operating system. It was buggy, it was slow, it was really just an overlay over DOS itself. And Microsoft had some license requirements with Apple. They had some agreements with Apple that prevented them from doing some things. For example, Windows couldn't overlap. So if you've seen original pictures, or if you've ever used some of the old versions of Windows, that might be something that you remember, where all the little windows are all kind of tucked up next to each other because nothing can overlap. Anyway, that original version used Paint and Write. It had a terminal, it had the game Reversi. A lot of this stuff is still in Windows today. In fact, I just used the Paint program moments ago as I was reviewing pictures to use in this lecture. So, Apple and Microsoft begin legal battles with Windows in versions 2.03 and 3.0. The judge eventually drops pretty much all of Apple's 189 claims, but they do leave 10 behind, but it turns out that most of them are uncopyrightable. So Microsoft wins this legal battle and is able to then proceed with creating true graphical windows in Windows. Windows 3 comes out in 1990, and it's wildly successful. They end up selling 10 million copies, even before some of the later versions, Windows 3 and Windows 3.11 and Windows 3.11 for work groups. Even before all of these come out, they've sold 10 million copies of this thing. Support only ended in 2001, so this is into the 2000s that this is still being used. So support for 32-bit software, because the original version of Windows was simply 16-bit, but 32-bit software begins in Windows 95, which does come out in Windows 95. And that's followed by a huge list of operating systems, all the way out to Windows 10 today. There's some great operating systems in here. Windows XP is phenomenally good. Not very secure, but a great operating system. Far, far better than Windows ME, the mangled edition. And it's continued all the way through 7, which was great, Vista that was terrible, 8, which I liked a lot, and now we have 10. So tons and tons and tons of different operating systems have come out, and where would we be if it wasn't for Windows today? A phenomenal piece of software. And not only has it been extremely well received, it is also made Microsoft incredibly wealthy. Bill Gates is the richest man in the world, and that is as of the beginning of 2017 that I'm recording this lecture in here. Not only is he the richest billionaire, around $75 billion, but he's also given away more than $33 billion, which is more. He and his wife given away more money than anybody else in history. So remember that when you think about the wealth that he's accumulated and the business decisions that he and Microsoft have made, that it has enabled him to give away $33 billion. So let's talk about macOS on the other hand. So Steve Wozniak and Steve Jobs, they found Apple Computer in 1977. They immediately began to make computers that were Wozniak's design. Wozniak is a true genius, a true electrical engineer and design genius. Their Apple I computer sells 200 units, even before Apple is founded. But the Apple II, which gets launched in April of 77, goes on to sell millions well into the 80s. I remember using Apple IIs and Apple IIes in school in second and third grade. Those things were everywhere, and they stayed around for a long time. They were very stable pieces of hardware. The IPO that Apple does in December of 1980 generates more capital than any IPO since Ford, all the way back in 1956, and it instantly made more millionaires in the world than any other company in history has ever had. So massively profitable and productive company. Apple visits Xerox PARC in a fairly infamous set of visits, and the jury is still out on whether or not Apple was stealing or is inspired by the designs here. Most people have settled on inspired in terms of what Apple comes away with from Xerox's PARC labs. Anyway, they come back with the ideas for Apple's first GUI computer, so the Lisa. And the Lisa had a lot of really forward-thinking innovations. It introduced the words mouse, desktop, and icon to our computer language lexicon. But the problem is that the Lisa cost $10,000 in 1983. So in 2016 money, that's almost $24,000. So obviously, the Lisa as a computer does not succeed. However, subsequent computers that they make are all very, very successful, and they're running their early versions of the macOS, which was a fantastic operating system to use. Very easy, very simple. It was really a pleasure to use. I enjoyed it very much. Interestingly, both Jobs and Wozniak leave Apple in '85, so they really weren't in it all that long. Of course, they were ultra rich, so that it's not like they needed to stick around from the monetary perspective, but they do both end up leaving. Steve goes on to found Next, and they start producing the Unix-based NextStep OS for all the computers that they were making. That particular operating system uses the Mach 2.5 kernel, and we're going to talk about why that kernel is important and why microkernels like Mach are important in general in the coming slides. So they also use a bunch of BSD tools in order to make this operating system. In '96, partially because of Steve Jobs' influence on Apple, Apple buys Next. and that beats out their rival BOS. And what happens there is that Jobs returns as the CEO to Apple, and the rest is history. So that kind of starts this meteoric rise of Apple. So I remember this happening, that at the time Apple was in trouble. They didn't have much money. They'd been involved for decades in legal battles between the two, and everybody was really tired of it. Microsoft was in. They had all kinds of lawsuits being filed against them, and partially to restore good faith, good working relationship with other computer makers, and also to help forestall some legal problems they have, Microsoft donates $150 million to Apple. And I remember this. It was just like, here, have a bunch of cash. Hopefully we can bury the hatchet here. And it turns out that is kind of where they turned the corner. So Next Step becomes the foundation for OS X, and that launches in 2001. So OS X is really, really important. Even though the sales of OS X are good, what really matters is what OS X turns into. So OS X launches in 2001 in version Cheetah, and nowadays, or at least in 2016, 10.12 is out, which is the Sierra version, which had a lot of user interface changes. So iOS, let's talk about where that came from. So when Jobs returns back to Apple, he brings with them a piece of software called WebObjects Application Server. And that they turn into the Apple Store. So internally at Apple, what happens next is that OS X is changed or is forked into iOS. So they keep developing OS X for their desktop computers, but they take iOS and or they fork it and create iOS. So it's still based on the Mach kernel and the BSD subsystems, but that operating system that Steve and his company developed when they were part of Next becomes the iPhone's operating system. They add to it capacitive sensors. This is part of the screen touch technology, and they generate what's most important, a new user paradigm. So they introduced, they weren't the first ones to do it, but they combined successfully in a sleek package this touch system. The file system has been hidden, so they take that away from the user, essentially making it a simple thing that anybody can use. And they include this web browser, as the web is taking off at this time. So the iPhone launches in 2007 and starts the smartphone revolution. So they originally just called it iPhone OS, but eventually they rename it to iOS. Just to make it shorter. But the App Store doesn't launch until July 2008, so it wasn't for another 18 months that came out. Anyway, the unit sales in 2016 for Apple's major products here. So in 2016, the iPhone, they were selling 200 million of these things. The iPad was selling 45 million, and the Mac computer, the desktop operating system, was 18 million. So their mobile devices make up 93% of their unit sales. So yes, OS X was important, but what it turned into was the real moneymaker for Apple Computer. Let's talk Android now. So Android is founded in Palo Alto in October 2003. Their initial plans, is that they were competing with Symbian and Windows Mobile, who both used to be competitors in the nascent smartphone market. And they were using a custom fork of Unix. They still are. Android is a fork of Linux. So what happens is that 2005, Google notices them and purchases Android Inc. Google did not design Android from the beginning. They purchase Android. They've never revealed the price, but we know that it was at least $50 million. So what Android was working on was something that actually looks a lot like the BlackBerry's operating system. Nowadays, BlackBerry is all but gone. But at the time, they were the player in smartphones. So BlackBerry's operating system has a full QWERTY keyboard underneath it. And what happens is that Apple does their announcement, their rollout of the iPhone in 2007. I remember that. I was a grad student here at OSU, and we were all crowded around watching the monitors and the screens, watching this phone come out. People were mixed in terms of whether or not it was going to have an impact, but everybody agreed it was by far the prettiest phone we'd ever seen. After Apple rolls out the iPhone, the Android designers scrap their plans where they were competing directly with BlackBerry and instead do the same thing Apple was doing. They go for a full touch screen with hardly any hardware buttons on it at all. And Android's first phone is the Dream that they partnered up with HTC, the hardware manufacturer, and that came out in October 2008. So fast forward today, and Android wins. So Android isn't just the dominant mobile operating system. Android has become the dominant operating system in all sales of devices worldwide. So from 2008 to 2015, this is what happened. So in 2015, Android devices that were sold, 1.3 billion devices run Android in 2015, of the ones that were just sold in 2015. So iOS and OS X, so mobile and desktop combined, is just under 300 million devices. So Windows is at 283 million, and everybody else, which includes a whole lot of custom stuff, is around 520 million. So according to Gartner Research, Android sales are 54% of all the sales that are made. Now, we're going to step back for a second and take a look at this, but one of the things that we notice is that all the devices here that are running Unix is a huge number. So the Android number is 54% added to the iOS and OS X number, gets us to 66%, and certainly a lot of the others that are running are also Linux and Unix-based devices. So Unix and its derivatives is by far the most common and most sold operating system in the world. Okay, so let's talk about booting up a PC. Before we can talk about what is happening down in the kernel, let's talk about how these systems actually boot. In the old days, so the ancient days of pre-2014, when you turned on a computer, it would load what was called the BIOS. And the BIOS stood for the Basic Input and Output System. And what the BIOS would do is that it'd do hardware initialization, including a bunch of testing on the hardware to make sure it was all working. It would test the RAM, it would test the CPU, it would test power, and make sure that everything was working. Then it would load up the bootloader, which simply then goes to load the operating system itself from, say, a hard drive, or it might pop up a menu that the user would choose the operating system from. But this bootloader would just grab the operating system and start it running. And the BIOS then provides this abstracted manner of getting data to and from the input and output devices. So instead of having to actually know about the characteristics of the hardware, you could read and write data from the BIOS layer, and the BIOS layer would handle the translation between hardware and the drivers. Nowadays, though, with modern PCs, what they first do is that they are going to load the UEFI firmware. UEFI stands for the Unified Extensible Firmware Interface, and it's a replacement for BIOS. UEFI is essentially a mini operating system, and it does a lot more. So first of all, it'll boot from large disks, including ones up to 8 zebibytes, and we'll talk about what a zebibyte is here in a moment. And it has a modern GUID partition table, a GPT. That's the partitions that are on a hard drive. So it can boot gigantic hard drives using modern partition tables on those drives. And this environment that it boots up is fully featured. It'll even give you a mouse and a keyboard. There's a graphical user interface in this pre-boot environment. It's got audio. It's got access to the network. It'll test the hardware. And IT people love them because it can phone home to the IT servers. It can report security, all that kind of stuff. They can even be turned on and off through this pre-boot environment system. So it'll give you the chance to boot the operating system of your choice from all the ones that are registered. And optionally, it can prevent, and this is actually controversial, it can prevent unsigned drivers from being used to boot that operating system. And what that does is it prevents firmware level rootkits. At least that's ostensibly the reason for why this is in there. But what had the users of Linux up in arms was that if Microsoft decided to enforce using this unsigned driver prevention system from locking the hardware down to a specific operating system, they could essentially make it so that only Windows could be run on that hardware, completely locking out Linux. Microsoft has never done such a thing. It would be, a horrible PR blunder, and Microsoft would not do that, and has not done that up till now. So that's a good thing. This fear has turned out to be unfounded, and this feature of UEFI to prevent these firmware level rootkits is a good thing. So you can still get rootkits, but UEFI has certainly made it a lot harder for those rootkits to be embedded all the way down in the firmware. That used to be something that could happen. You could get a virus in the BIOS itself. Alright, so what's a zebibyte? Well, a megabyte is 1,000,000 bytes, and specifically a megabyte is 1,000 squared. That's where that number comes from. So a gigabyte is 1,000,000,000, a tera is 1,000,000,000,000. Here's a petabyte, that is 1,000 to the 5th. An exabyte is 1,000 to the 7th. A zettabyte is an exabyte is 1,000 to the 6th, and a zettabyte is 1,000 to the 7th. So what is a zettabyte? A zettabyte is 1 trillion gigabytes. So think how many gigabytes you have on your computer. Maybe you've got a terabyte of data on your computer, so maybe you've got 1,000 gigabytes on there. Maybe you've got 2,000 gigabytes on your computer. But a zettabyte is 1 trillion gigabytes. So a zebibyte is what happens when you are calculating the number of bytes by in powers of 2, so 1024 to the 7th. And this same type of nomenclature extends all the way back through the rest of the types. So a mibibyte and a gibibyte, that kind of thing. So anyway, this is now 1.1, whatever the heck this number is, but it's 1024 to the 7th is a zebibyte. Alright, so these UEFI can boot huge partitions, so that's a good thing for the future. Internally then, for Windows, a user can access the operating system using the Windows API, which is a very large system. There are lots of versions of the Windows API running at the same time. You can access Win64, which is the current version. There's Win32, which is the 32-bit subsystems. But you at least used to be able to still access even the 16-bit systems that were in Windows. Backwards compatibility is a big thing, so having all those different subsystems available is a big part of Windows. So the user has access to very, very low-level aspects of the GUI, which means that if you want to write a Windows program, if you're not going to use the big API libraries that will display those windows for you automatically, like .NET or DirectX for games, if you don't want to use those, then your Windows programs are gigantic, because actually spawning a Windows window is very, very hard, which is why most Windows programs these days are written using the .NET libraries, such that the programs themselves can be very, very small. The .NET binaries are, of course, gigantic, but those are installed with Windows, so it's no big deal. So there's going to be a lot of services that are running on top of the kernel that give access to all the different features of Windows to the user programs. So these are all the features, or all these services are things like the print spooler, which manages print jobs, and the audio manager, login systems, that kind of thing. So let's talk about the registry for a second. The registry is a much maligned database that is a hierarchical database of config settings, and it's used by Windows and in applications. One problem with it is that applications tend to not clean up after themselves, and the registry gets bloated and big and hard to analyze, and bugs or incorrect entries in the registry can cause the computer not to boot. So the registry gets used by the operating system in the sense that the kernels and the drivers and all the services that are included on the thing, and services are what Windows calls daemons from the Unix world, even the security system, the user interface, they all use the kernel, or the registry, to manage configuration settings. Individual applications can use the registry if they want to, but they can also just use config files on the file system. Oftentimes, programs that are written to be that can run on multiple operating systems will simply use config files, because using the registry is very Windows specific. So there's also another subsystem called the Security Account Manager, or SAM, and that is an encrypted database file that stores the hashed passwords and all the local accounts. You can't mess with the Security Account Manager while Windows is running, though you can do some trickiness with dumping the in-memory passwords. But the point is that you can edit the Security Account Manager file when Windows is not running. So in a previous lecture, we talked about the Windows password and registry editor, and it essentially accesses the Security Account Manager from a booted Linux partition and allows you to edit and change the passwords that are on the drive. This is one of these diagrams that are, these diagrams are drawn and shown and used in presentations all over the place, but they're not really very useful. This is kind of an older one that tries to just identify all the different systems and how they connect. For our purposes, the actual individual little connection arrows and what's what isn't all that important. The bigger thing that's important is just to see the major groupings. So from the user's perspective, there are a lot of systems that are exposed to you directly. So the login systems, spool servers for print, all the various services, service host applications, Windows Explorer, which is the actual GUI that's running, a task manager that can be used to open and close programs. So all these different things that you might be using are contained in and are part of the NTDLL, which is kind of this master file, this dynamic linked library that can be used in lots of different places. Down at the bottom is the kernel, and the kernel is going to interface with that hardware abstraction layer to actually manage the system. Interestingly, over here, the graphics drivers are shown to touch all the way down directly to the hardware, and that's on purpose. So graphics drivers and say games often like to write directly to hardware, bypassing the entire operating system, the abstraction layers, and everything. And that's just trying to eke out a tiny bit more speed out of this hardware. So I'm not a super fan of these types of diagrams, but at least they've got all the different terms on them so we can look and see how they are how they're relatively arranged. I mean, this one still has an OS2 listing on it, so it certainly can't be that new. Interestingly, Windows has had POSIX stuff for a long time, so don't be surprised that you see some POSIX entries in a Windows internal architecture diagram. Boot procedure for Windows looks something like this. There's going to be a power on, so power is applied to the system, and then the UEFI programs are going to be executed. So the UEFI system is booted and is run. And once it's up and Windows is chosen to be started, then the Windows bootloader, which is called winload.exe, it's going to load those basic drivers that are required. And it's going to read all that data from the disk and start to get them up into RAM. The kernel gets initialized and started, and then the registry and all of the non-boot drivers, so the ones after the system boots, those all get loaded into memory and started up. Then winlogon.exe starts, which is going to ask the user to log in. Once there has been a successful login, explorer.exe gets started, which again is the full GUI that is being used in Windows, and then the desktop window manager, the DWM system, is what is actually displaying the various windows that you're using as a user. Let's talk about the macOS for a second, and we're going to look back into history, into ancient history, about kernel architecture. So the Unix paradigm is that there is lots of little programs that interact with each other. And these little interacting programs talk to each other through pipes. And what pipes do is they allow data to be moved between these little programs, which causes to be implemented blocking system calls. So data is written into one pipe, but maybe it's not read right away, so the pipe blocks the other process until the data can be cleared. That causes data to be moved around in a staggered fashion around the system. So while it makes for a simple operating system, it isn't very good in terms of speed. So the implementation of these pipes as memory buffers, for example, which copy a lot of data around, that really doesn't scale very well when you want a fast speed. So when you need low latency and your kernel is spending all its time waiting blocked in system calls, that is a lousy kernel. So one of the responses in the 80s to fix this was to take the kernel and all that core functionality and write it as a single large nasty program. And we're doing that so that we can prevent we're trying to prevent the copying of data through this pipe system. We just want to have all the different pieces of the kernel be part of the same executable, so that we can just run them directly and not have to copy data between programs. But those large kernels are really bug prone. They're hard to write. The Unix system of small interacting pieces is much easier to test and is much easier to verify that those pieces are doing what we want them to do independently. So the outcome of this is that new theories of kernel design get tested out as part of the Aleph kernel. And the Aleph kernel was developed at the University of Rochester in '75. And what they did is they took the kernel and shrunk it down such that it was only handling access to the hardware, including the memory. So it's using a form of shared memory to copy information around between all these different subsystem programs that are out there. So what does this mean? Essentially, we're saying that the kernel only accesses the hardware, and it changes memory management such that we introduce a system called copy on write. So these CPUs that are developed here have support for a little module called the Memory Management Unit, the MMU. What that does is it allows for virtual memory to be implemented in hardware, tracking all those different pages of memory that are used by the processes. When you're doing that, what you can do is that when a system is told to copy data from place to place, it returns basically immediately saying, okay, that data has been copied, but all it's really doing is just telling you that virtually it's been copied, that it just gives you a reference that says, yes, that data is there. And if you read from that location where you just copied memory, it returns and says, yep, there's your memory, it's been copied. But the difference is that it hasn't actually been copied. It hasn't gone through the time to actually do it. The only time the data actually gets copied is if you try to write to that location. And when you do that, then it finally commits the data down to the system. And that's called copy on write. So copy only if you're going to make a modification. All these developments produce what are called microkernels. So tiny little kernels that are very, very fast, that tie together all the different systems, that work because of copy on write and this virtual memory management system making the memory access be fast. So the macOS uses the Mach version of the microkernel, and they pair it with these BSD programs. So these are basically BSD is a Unix fork, and they take these Unix programs and bundle them with the microkernel and produce their system that they eventually sell as the macOS. So a user program can access the macOS system by using all the Unix API calls that we've been talking about. So write and open and all that stuff. That's all stuff that you can do as part of the macOS because it's very, very Unix-like. So there are also additional Apple-specific APIs that you can use to access the operating system. So the graphical Windows environment, all those kind of APIs. So drivers are simply a form of what are called kernel extensions in Apple land. And those kernel extensions get loaded when the operating system boots. So you can have very, very trusted low-level code added down all the way into the kernel by third parties that boots with your system. So that's pretty handy for systems that need secure access. If you really need software that starts up before anything else does, you can add that down to the kernel with these kernel extensions. Is another one of those kind of silly graphs that mostly just splats all of the terms onto the screen. The broad categories here is that the GUI itself, the user interface system that Apple is using, they call Aqua, and the APIs that are used in that the user can access to operate different portions of the operating system. So whether it's the BSD systems you're using, Apple Classic, all this different stuff, even Java, all that connects to the core operating system where the kernel is, and the kernel, of course, is interfacing with the hardware. So again, not a fan of these things, these graphics, but at least they put all the different pictures, or they put all the terms in one place. The boot process for the macOS, you turn the power on, then our UEFI program kicks off, control gets passed to the bootx bootloader, and when it has finished loading everything in, it's going to load in the previously cached list of kernel extensions, which includes all the drivers. The init process that's in the Mach microkernel, and it's the same init process that we've studied before, but that init process gets started up, and we know at that point that the firmware is no longer, driving the bus. It's now up to the software being copied from the drive. So the Mach kernel and all the BSD data structures get initialized, input-output starts up, the kernel starts virtual memory management routines, and then the kernel starts up the GUI and the daemons and services for actual user interfacing. So Unix. Unix is run on a truly enormous number of devices around the world today. So it's generated fortunes, it's saved lives, it's been a truly positive agent for change for millions and millions of people. You can even run a bash shell in Windows 10 these days. So let's take a look at some of the connections between Unix and all the different variants that have come from it. So this graphic, this is a Creative Commons graphic. You can find it on Wikipedia. This is showing us connections from the original Unix operating system. So all the way back in '69, as we've talked about earlier, we have our PDP-7 based operating system, which eventually turns into Unix. Unix goes through a few different forks with a combination of mixed and shared, some open source code, some closed source code, and some shared source code. Creates the Unix, the main Unix trunk, and then we have the BSD fork that comes off it as a major change. So this is where Unix exists. It exists kind of back in the past as an actual operating system, but what generates from it is where we are today. So we can see down here that from the closed source systems, we can see that BSD 4.3, here's the 4.3 version of it, which again is a fork of Unix itself. BSD is forked to become NextStep. This is Steve Jobs' operating system that was created by the Next company that eventually turns into macOS. So here's macOS that we use today. So we also can see Linux over here as an open source system, and famously, Linux has no lines that connect to it. And that's partially, it's mostly because Linus Torvalds writes his kernel to be a clone of another system. He doesn't use other people's code, he clones what other people are doing in terms of its interface. The Sun OS, which has not been around for a long time, but the Sun OS is another fork of BSD. Those of you who are familiar with Solaris, Solaris is one of those forks. We've got UNIXware, the System 5 releases, the System 3, 5, these are actual Unix. This is the actual Unix fork, but they'd commercialized it by this point. And then we have HP's own HPUX system, HPUX. And a lot of this development was done right here in Corvallis, where Oregon State University was. In fact, my father, John Brewster, was instrumental in the development of HPUX through the late 80s and 90s. Let's take a look at Linux. So Linux connections. This is another graphic that's Creative Commons. It's currently hosted on Wikipedia. Fantastic graphic. I highly recommend you check this out. You can zoom all the way in and look at all these different forks of the various Linux distributions that are out there. Each one of these little lines is another Linux distribution. Many come, many go, but there has been an awful lot of development based on Linux. The massive success of Debian out here, Slackware, one of the oldest ones, the Red Hat family, the Gen 2 group here, here's Arch Linux, and then the etc. Just tons and tons of little one-off distributions. You too can grab the current copy of Linux, the kernel, and make your own distribution. Go for it. There's nothing stopping you. Release your own distribution and see what you can do with it. We can even see Android over here on the side. So for all of its successes, it's relatively new. So let's talk about some of the, or at least mention briefly, some of the pioneers in all of this. So Colossus in '44 was designed by Tommy Flowers. This is during World War II. It was the world's first programmable electronic computer, and it was designed in wartime to help decrypt German messages. By the time '46 rolls around, we have the ENIAC, which is the first all-electronic Turing-complete computer. That means this computer can solve any problem that is solvable by computers. They also produced the UNIVAC, which was the first commercially available computer. These systems are amazing, right? Building-sized computers full of vacuum tubes, incredibly slow, have to be basically rebuilt every time you change them, but they are all electronic and they're fully Turing complete. So another wonderful lady named Margaret Hamilton, who actually just won an award for, I think it was like a Lifetime Achievement Award in software engineering, but she coined the phrase software engineering. She was extremely important in timing critical human interaction and the testing of those software systems with computers. She was the one who led the development of the onboard software used in the Apollo moon missions. So we got to the moon because of the hard work of Margaret Hamilton and the teams that she was leading. So we wouldn't have gotten there without that critical software that she and her teams designed. And one of the first operating systems that actually has a software-based virtual memory system was a system called THE. And it was designed by a wonderful guy named Edsger Dijkstra way back in 1962. So this has been around for a long time. So let's look at Dijkstra for a sec. He died in 2002. Some of his contributions were the famous Dijkstra's algorithm for finding paths in a graph. He came up with semaphores, including mutexes. If you're familiar with the Dining Philosopher problem, deadlock, and all these other synchronization issues, that was all the work of Dijkstra. So he did a lot of operating system design itself, and we just looked at that THE, or at least I mentioned the THE system, which we'll talk about here coming up. He generated a lot of initial work in abstraction layers to help differentiate individual layers that you are working with at any given moment in operating system design. He did a lot of compiler design also. In fact, he was trying to create a compiler for Algol 60 and decided that he wouldn't shave until he'd finished, and then after he finishes, he decides to keep it his beard anyway. So this, the start of these UNIX beards, right, which we've talked about before, the pioneers had them too. So in software engineering, Dijkstra is the fellow that caused this belief that GoTo is an evil thing. So he was trying to shape programming as a mathematical discipline. It is not just some ad hoc craft that's all informal and fast and slick. He was trying to make formal specifications, formal verification of programs be part of the system. He is trying to show how to simplify these things in terms of their He's trying to simplify them down to the mathematical operations that govern what was happening. So the GoTo statement, which essentially allows these unconditional jumps across your code, he writes this paper about being anti-GoTo. So if you've ever had your teachers say don't use GoTo, it's because of Dijkstra. So let's talk about THE for a second. This is the system that Dijkstra worked on. So these are the layers that it had back in 1968. It had a scheduler, it had a memory pager, communication between the operating system and the terminal that the user would use. So this is moving from the kernel outwards towards the user. Layer 3 here would be managed input and output between all the devices. Then we had user programs, and then layer 5 he famously said was the user and that it was not implemented by us, which is certainly true. Dijkstra didn't create people, but what are you, dear student, going to do with the implementation of yourself? What are you going to do? So allow me to wax philosophical here for a moment. So some of the quotes from Dijkstra. He said, "Brain power is by far our scarcest resource. The competent programmer is fully aware of the strictly limited size of his own skull. Therefore, he approaches the programming task in full humility, and among other things, he avoids clever tricks like the plague. Simplicity is prerequisite for reliability. And finally, programming is one of the most difficult branches of applied mathematics. The poor mathematicians had better remain pure mathematicians." So computer science as a department here at Oregon State University used to be part of the mathematics department. And eventually CS moves into the College of Engineering, but CS used to be a component of math here at OSU. Let's look at a longer quote. So he gave a lecture at the ACM at one of the big ACM meetings in 1972. And this is what he said. He said, "There may also be political impediments to becoming an exceptional programmer. Even if we know how to educate tomorrow's professional programmer, it is not certain that the society we are living in will allow us to do so. The first effect of teaching a methodology, rather than disseminating knowledge, is that of enhancing the capacities of the already capable, thus magnifying the difference in intelligence. In a society in which the educational system is used as an instrument for the establishment of a homogenized culture in which the cream is prevented from rising to the top, the education of competent programmers could be politically impalatable." Let me conclude. Automatic computers have now been with us for a quarter of a century. They have had a great impact on our society in their capacity of tools, but in that capacity, their influence will be but a ripple on the surface of our culture, compared with the much more profound influence they will have in their capacity of intellectual challenge without precedent in the cultural history of mankind. So let's zoom into this a little bit more here. So the first effect of teaching a methodology rather than disseminating knowledge. That's something that I, in particular, and the department in general, is trying to do here. We are trying to teach computer science as a science, to give you the theories that you need so that you can acquire any skill later. So what Dijkstra is worried about is that he is acknowledging that we are trying to teach methodologies, not just disseminate knowledge. This isn't a trade school. We're not interested in teaching programming per se, but we're interested in teaching the theories that cause programming to make sense. So, in a society in which the educational system is used as an instrument for the establishment of a homogenized culture, what he's talking about here is that he was worried at the time that the political implications of teaching people to create fascinating software that is incredibly useful would cause people to be viewed unequally. And he's worried about that. He is not interested in giving out participation trophies. He is interested in making sure that people are allowed to excel, that we can reward winners, that we can reward victors. Life doesn't hand out participation trophies, and he was concerned at the time that programming might be something that gets locked down by the government. So the last statement here that I wanted to talk about was how the impact for computers on our society in their capacity of a tool. So yes, computers are wonderful tools, but what are you going to do with that tool? Here he's saying is that what we've seen so far is nothing compared with what it can do for us in terms of the challenge that it can present. Are you going to take the skills and software that you've learned and go create a clone of Facebook? Are you going to go create a social media network of some kind? Are you going to go create a patent troll that simply uses your computer skills to try to extract money? Or are you going to take the education that you've received, that you've worked so hard on, and write software that gets people to the moon? Are you going to be involved in machine learning that helps figure out ways to preserve water and help distribute resources for those in need? Are you going to do something useful out there instead of just living life? So attempt to improve it. And that's what Dijkstra is saying here. Well, I sure have enjoyed working with you throughout this course. I hope you've enjoyed it too. If you have any questions for me, feel free to hit me up on the discussion boards or send me an email, and I'd be happy to help. Have a great day, and thanks again. Bye.